All right, hello, my name is Foster Grafe. I'm presenting today on domain coloring. As I was thinking about a topic involving complex numbers, I was looking for something maybe related to art and ways to incorporate art in mathematics. And I saw some things dealing with domain coloring. As I learned more and more about it, I realized that domain coloring is just a very practical tool to start solving a problem that we encountered in this course. And that problem is really, how do we graph complex functions? Because obviously the problem is that in the real world, we have two axes, and one can be the input and one can be the output, or the independent and dependent variable. But in the complex world, the input already has two parts, right? And so the two axes we have just have to go towards an actual number, and how do we then plot the output? And that's ultimately what domain coloring, attempts to come towards solving, and I think can help with that in some interesting ways. And what they then do is in order to do that, you have to have some understanding of kind of how colors work. If you've ever worked with trying to edit with colors, you know that there's typically three values that people go with it. You can go with the R, B, and G values, or you could go with H, S, and L, like hue, saturation, and lightness. There's also H, S, and V. As I was learning about domain coloring, it's very common to go with H, S, and L, although you could certainly really go with each one. But it's about saying, well, a color has three components, just like a complex number has two components. We really only need two components for the output. So as I look at something like, H, S, and L, I really only need to use two of those three. And I'll use one of them for my real part and one for my imaginary part. Or we can go with polar form, which is actually what we'll do. But what you could do if you wanted to is you could say, well, one of these three things will represent the real part of our output. One of these three things will represent the imaginary part of our output, and then the third thing we would just keep constant. People don't typically go that route just because there's probably not as much of a pattern as you move through colors when it comes to hue and saturation, where you would be placed in terms of vertical and horizontal placement. But there is very much a relationship. The hue of a color is literally a circle. It's 360 degrees. It's based off the color circle. So that goes really well with angles. And so oftentimes, if we're going to work with this, we would say that the hue, which is the H value, just represents the argument or the angle associated with, your output. You could go with lightness. It typically works out nicely to use as well, and you'll see how as we go along it. Sometimes people go with the lightness is the modulus of your output. A lightness operates on a percentage scale, so it goes from 0 to 100 in terms of a 0 would be basically black, a 100 would be light or white, and then in between is whatever color you're at, and well, that depends on your hue. Right, your hue could be anything along the color spectrum. And then there's saturation, and oftentimes we just leave that constant. And you could leave it constant 100% and just leave it like that. And so now if you want to look at a function like f of z equals z plus 2, something really simple like that. And let's say my input here is, 2 plus I, right? Well, then my output would be 4 plus I. So what I would do is at the value on the axis of 2 plus I, which would be here, instead of putting just a black dot, I'm going to put a colored dot, right, that would be associated with something in that area of the color zone. And so what I would then do is say, well, what's the output there? The output of 2 plus I would be 4 plus I, because my function is z plus 2. And so what's associated with 4 plus I? And that's where you would say, well, we would need to figure out the polar form of that, basically, right? And once you determine what that is, you get your angle and you get your modulus, and that's the color you're going to place there, right? Just for simplicity's sake, I'm going to start, posting some maybe along the real axis. And so to think for a moment, what lies along the real axis, that would be anything with an argument of 2 pi or 0. Something like here, I could plot a point here and I could plot a point there. This would have L equals 5, this would have L equals 1, but they both have H value of, let's just say, 0. What I'm going to do is I'm going to show you really how the color spectrum kind of works here. As I go to edit colors in this tool, you've got your color spectrum here, and what you'll see is that as I like move along here, you see horizontally I move left to horizontally I move and I'm changing the hue. And so over at a hue value of 0, I'm basically in the red area of the color spectrum. And as I continue to increase my angle in this case, I'm moving towards yellow and then green and then hues of blue and then eventually to purple and then eventually back to red once I start to approach that 360, or in this case 2 pi. And that's just simply moving horizontally. You can see as I move vertically, I'm changing my saturation. That's just basically, keeping you in the same form of color, but changing it up a little bit more. Saturation and lightness are very related, and we could just change our lightness over here. And you can say basically as I have 0 lightness, I'm very dark. If I have 100 lightness, I am very white. And in between, I am different, tones of the color that I'm at in terms of hue. And so that's, kind of what you can go with and help you out there. So as I look at that, I'd say, well, what should the color of the dot be at 1 and 5? Well, the hue should be basically 0 or 360, which is basically some version of red. And how do I want to handle that lightness? Well, here, lightness goes from 0 to 100. And so that you might have to adjust based off the scale of your graph, right? And so maybe you think, here, let's just have, maybe go by tens. And so like if I'm at, for that dot at 1, that has an L value of 1. Well, maybe I just treat that as an L value of 10. So as I go with a hue of 0, a saturation of 100, and a lightness of 10, you can see that I still ultimately have a pretty black dot, but it is a little bit closer to red. Now as I go back there, and now at the value of 5, I still am at a value of 0 or 2 pi, which is still in that red zone, but now I'm going to change that L value to 50. And you can see I'm much more brighter red at this point, right? And so, and then as you imagine, as I move out this way, I am continuing to get lighter and lighter and lighter, right? Of course, that's going to change then as you start to introduce functions, right? And so I just want to kind of give you a sense of what that looks like. You have to have a sense of how the colorings work, of how HSL works. Here I think is a good representation of the color wheel. And so you can see that again, as you get further and further inside or further and further close to 0, you're very dark. Further and further away from 0, you're very white. And then as you get more and more used to like domain coloring, you kind of like understand of what it means to be reddish or yellowish or purplish or bluish, and where that would put you in terms of, what angle, right, or what your theta value would be. So, just as some examples to have you look at, I was looking around at some tools that you can use to do domain coloring, and I found this tool on GeoGebra, and it's kind of slow, but for example, here is here's a bit of a tool that they have for you. In fact, I'm going to go to, it is a little bit slow, so I'm just going to, just a second, as I go to domain coloring, I'm going to go to HSL scheme simply. So you can see they have HSL, HSV, RGB. Those are just depending on how you want to use it. But what this also does is it gives you a bit of a sense of like, you can drag this dot around and kind of see what the colors look like for those particular complex numbers, right? So that can kind of help you out a little bit. But what I'm going to do is, as I move to HSL and HSV schemes, I'm going to go to HSL. And what you can do is you can put in a function, right? And so I can just start by putting in like f of z equals just z, and we can keep it very basic, right? And then it's going to start kind of creating this. Now you'll notice that they're working with some sort of scale here as it's moving out. This is really only looking up at like running from values of -2 to 2 in the reals and -2 to 2 in the imaginary. But there's certainly some other type of scale going on here. But as it comes out, you're starting to see a little bit of what that kind of looks like, right? And it takes a little bit of a while on this tool, but you can start to graph it a little bit and have a sense of what that function is resulting with. So this is just basically the set colors for every complex number. And I can put in a somewhat of a more complicated one, and maybe it's 2z plus 5, and then I can click in, and I'm just gonna jump ahead here as it takes its time forming, but you can kind of see that it looks a little bit different than what we initially saw when you double the complex number and then add 5 to it. So I've jumped ahead a little bit here, and you're kind of seeing the big shift that happened because of that adding of 5, right? And so you can get a bit of a sense of what's going on there. Let's try to do like a modulus. Let's try to say that the function is the modulus of z, right? And this is, I think, is a really interesting one and gives you a really real sense of what's going on with this, because what you're going to see here is there's mostly only going to be reds, and I'm going to jump ahead here again. So as this kind of comes out and continues, we see it's pretty much just all certain shades of red, and when you think about it, that makes a lot of sense, right? Because a modulus always results in strictly a positive real number. And so when you're a positive real number, you are consistently at a theta value of 0, right? Which in the hue shape, that's red. And it's just a matter of saying, you know, the shorter the modulus is, or the smaller the modulus of the complex number, the darker that red will be. And as you get further and further away from the origin, the lighter it's going to become. But it all basically stays red. And I could change this, and I could maybe multiply that modulus of z by I, and you could think about then what that would result in. Well, that didn't turn out as nice as I thought it would. Sorry, the reason it didn't turn out as well as I thought it was because I forgot that when you do multiplication, you need to throw in that asterisk to serve as the multiplication symbol. So we're just writing I next to modulus of z wasn't good enough. But now you can see it's very, very similar. It's just a shade of green, because now you're dealing with something that, you know, modulus of z is strictly a real number. Multiplying it by I makes it strictly a positive imaginary number, which then puts it up at pi over 2, which, you know, in the hue world, that would be an angle of 90, and that would put you, you know, and we can move back to the color circle itself, and you can see, yeah, when you're up there, you're in the greens. And as you know, obviously, if you had a really good sense of how colors work, you'd be able to look at a graph and interpret it a lot quicker than probably I am just right now. But basically, I thought the tool was interesting. I thought it was an interesting way to represent graphing of functions, because I was always just kind of like, well, how do we really deal with this? And now we can kind of get a sense of what these functions might look like. And as I was kind of looking around, I saw some really artful things that I thought were interesting. As I was just looking at the Wikipedia page for domain coloring, you can kind of see here like what people might use, and these are working with different types of scales. You know, there's simply f of z equals z, and then you've got f of z equals z to the third minus 1. And then up here was a really, really interesting one. This is f of x, but they're using x squared minus 1, x minus 2 minus I squared, all over x squared plus 2i. And you're seeing all sorts of really interesting things. And what I really find interesting is these all of a sudden you kind of have these moments where there's like it's kind of trending towards green, and then bam, it's black or dark for a while, and then it gets back to green. And think about what that means. That must mean it approached 0 quite suddenly, right? Which, you know, happens all the time with functions. And then you look at these white stripes, and that must be moments where it turns maybe, you know, trends towards infinity very quickly, in terms of at least the lightness value, trend towards infinity or 100 very, very quickly. And so, you know, somehow when you graph these functions, they can turn out really artful. This is one that was in the news that I thought was really interesting. It was an honorable mention in illustration, and it was someone submitted this to an art show and got an award for it. And it's just a graph of a complex function. But you can kind of see, you know, where the singularities are happening, where you have these white circles and when these dark circles are happening, and kind of how that all turns into something pretty artful. So I liked it in the sense of kind of having a practical way to graph a complex function, but also how you can now have a graph that turns out to be, that can look really, really cool. It's certainly harder to interpret, harder to understand what's going on. It takes a lot of thinking, a lot of understanding of colors. But it is pretty cool how they can look at the end as a product. So anyway, thank you for taking the time to watch my video.